So here's the schedule. Today, Friday, the 28th of April, 2017, we are going to just be exploring about this new topic that I mentioned the other day called Laurent series. So we'll be trying to do lots of calculations, visualizing some things in Mathematica. You may want to have Mathematica notebook open. I don't have this one online, but you may want to have one open and just experiment with me. So I will save this. I did post the other days up on Moodle under the post-class notes, I believe. And then next Monday, we'll review for the test. Have the test next Wednesday. And then after that, we've got officially 7 more class periods after that. I think the last week of class, though, I think Monday and Wednesday that week, I'm going to probably not have class, and you'll have time to work on the project. And I'll be available for consultation about the project during our class time that week, and perhaps other times as well. Friday that week we'll review for the final exam. So we're going to end up with content after this third exam in chapter 6, where we focus on what's really going to be the main application, and that is to evaluating real integrals that really can't be solved really any other way besides complex analysis that I know of, at least. So that will finish up our semester. There's probably about 2 to 3 sections in chapter 6. All right, so I think exploring Laurent series expansions is going to take us pretty much the whole time here today. Depending on how fast I can do this, one example may take the whole time, because one function I should say. We're going to take one function and expand it in many different ways as infinite series. Let's let the function be z over z squared plus z minus 12. So there's a rational function. It's got 1, 0 at z equals 0, and it's got 2 poles. You can factor the bottom as z plus 4 times z minus 3. So the poles are at -4 and +3. If this is the complex plane, and 3 is here, and -4 is over here, those are your poles for this function. Okay? All right, so again, we're going to expand this in many different series, centered at many different points, or well, maybe just a couple different points. First, I'd like to find its Taylor series centered at 0, which is the root. I'd like to find the Taylor series for it. In all these situations where we try to find these series expansions, it's going to be helpful to do some tricky algebra, some algebraic manipulation to try to use the formula for a geometric series, which I will again put up here for reference. A plus AR squared plus AR cubed, etc. converges to A over 1 minus R if the modulus of R is less than 1. We're going to make use of that a lot here, okay? After doing some tricky algebra, that takes a lot of practice to get good at. And I'm not really an expert at it. I need practice myself with it. First, Taylor series. There's a couple different ways we could try to approach it to find the Taylor series. We could try to find the Taylor series for this function, thinking of it as a product. Say z over z plus 4 times 1 over z minus 3. We could find the Taylor series for each of those and multiply the Taylor series. Perhaps what's a little simpler, I think we will check it this way. Perhaps what's a little simpler is to expand it as a sum of 2 fractions, something over z plus 4 plus something else over z minus 3. In other words, use partial fractions. Can we write this function as some constant a over z plus 4 plus some other constant b over z minus 3? The answer is yes, you can. And the quickest way to solve for the coefficients a and b would be to say, I'm looking at the equality between these two things here, would be to say multiply both sides of that by the common denominator z plus 4 times z minus 3. With this thing, you get complete cancellation on the bottom. You get just a z. Multiplying that term by z plus 4 times z minus 3 makes the z plus 4's cancel. So you're left with a times z minus 3. Then multiplying this thing by z plus 4 times z minus 3 makes the z minus 3's cancel, and you're left with b times z plus 4. You want this to be true no matter what z is. And the quickest way to solve for a and b then is to plug in special values of z that make these terms go away. You might wonder, I mean, that would be 3 and negative 4. You might wonder, is that valid since that's where this function was undefined? It turns out it does work. So let's go ahead and do something that works. If we plug in z equals 3, for example, on the left side we get 3. On the right side, the a term goes away. We get 7b, and therefore b is 3/7. If we plug in z equals negative 4, on the left side we get negative 4. On the right side, the b term goes away, and we're left with negative 7 times a. Double check my algebra here. So it looks like a is positive 4/7. We can check this on Mathematica symbolically with the command apart. Let me go ahead and enter the function here. I'll enter it the way I originally wrote it, as z over z squared plus z minus 12. If I use apart f of z here, that will break it into partial fractions. And we can see the a is 4/7. That's the constant above the z plus 4, and we did get 4/7. And the b, we got to be 3/7, just like we see here. Okay, so it looks like I did it right. All right, so let's now find what's really the Taylor series expansion for both of those functions individually, and then we'll combine the Taylor series term by term, which is valid. Basically, within the domain of convergence, at least the open domain, if we're not considering what happens sometimes at boundary points, you can do anything you want with these series. You can integrate them term by term, you can differentiate them term by term, you can add them, you can multiply them term by term, and it all works out nicely. There's no worry about something strange happening. So let's first look at a, which was 4/7 over z plus 4. I'd like to expand this in a Taylor series about z equals 0, which will actually also be its Laurent series about z equals 0. Sometimes the Laurent series equals the Taylor series. Trying to get it into the form something over 1 minus something. What kinds of algebraic tricks can I do to get it in that form? Well, if that were a 1 instead of a 4, I'd be close to being done. So make it a 1 by factoring the 4 out. And you can bring it up here and write it as 4 over 7 times 4. The 4's cancel. You get a 1/7 on top, and you can write the bottom with a little bit more tricky algebra as 1 over, or 1 minus negative z over 4 in parentheses. So I factored a 4 out of the bottom, giving me in the bottom 1 plus z over 4. I put the 4 up on top in the denominator there next to the 7. I canceled with the other 4 there. And I also wrote the 1 plus z over 4 as 1 minus negative z over 4, so that I can get it in this form right there. So it is now, can be thought of as the sum of the geometric series with a equal to 1/7 and r equal to negative z over 4. So I get 1/7 plus 1/7 times negative z over 4 plus 1/7 times negative z over 4 quantity squared plus 1/7 times negative z over 4 quantity cubed, etc. That can be simplified, if you like, to 1/7 minus 1/28 z plus 4 squared 16. 16 times 7, what's that going to be? 10 times 7 is 70. 6 times 7 is 42. 112, is that right? 16 times 7. You can have your calculator out. Here. I might check some of the calculations on Mathematica, but if you can have your calculator out to double check some things. Somebody tell me 4 cubed times 7. 448. Is that right? Okay. Etc. There we go. There's the Taylor series expansion for this function about z equals 0. It doesn't converge for all z though, right? We get equality if the common ratio in modulus is less than 1. I can get rid of the negative sign. I can also multiply both sides by 4. The modulus of 4 is 4. This is equivalent to the modulus of z being less than 4. Which it would have to be, because for that function, I'm not talking about my original function here, but for this function, a over z plus 4, 4/7 over z plus 4, there's a pole at negative 4. If we're expanding about 0, it's going to be analytic on the biggest open disk it can be, up to but not including the pole. It would have to be a disk centered at 0 over radius 4. When I now do it for the other one, where we're dividing by z minus 3, I'm going to get a radius of convergence of 3. And when I add the two series, I got to take the smaller disk, where they both converge. Let's do the other one next. 3/7 over z minus 3. I'd like to make that negative 3 a 1, so factor out of negative 3. Cancel with the 3 up there to leave you with negative 1/7 up top. If I factor a negative 3 out of z, what do I get? Z equals that. So when I factor a negative 3 out, I'm left with minus z over 3. Right? If you're not sure, try going back the other way. Multiply the top and the bottom by negative 3. That times negative 3 is positive 3/7. This times negative 3, you get a negative 3 there, you get a positive z there. This works. That was checked for. Again, now we have it in the right form. A over 1 minus r. A is negative 1/7. R is positive z over 3. Negative 1/7 minus 1/21 z minus 9 times 7 is 63. 1 over 63 z squared. 3 cubed is 27. 27 times 7. Do that for me. 189. That's valid if the modulus of z is less than 3. If negative z over 3 and modulus is less than 1. Yeah, now combine these two series to get the series for the original function that will be valid on the smaller domain, which is where the modulus of z is less than 3. The intersection of the two domains. So let's see. Add these. I'm looking here and here. Okay, the 1/7 cancel, as they should, because this function has a 0 at z equals 0. If the constant term were not non-zero, then that wouldn't be true. Yeah, the constant terms could cancel. So there's no constant term. What about the z power term? Negative 1/28 minus 1/21. We do it as a plus on Mathematica. 1 over 28 plus 1 over 21 is 1/12. So we get negative 1/12 z, it looks like. 1/28 plus 1/21 is 1/12. I've got the negative signs there. Next one, I've got 112, 1 over 112 minus 1/63. 1 over 112 minus 1/63, negative 144, 1 over 144. That's the z squared term. Let's go one more. What about the cube term? Negative 1 over 448 minus 1 over 189. Already forgot it. What is it? 1 over 448 with negative signs. I'll do it with positive signs here on the computer. Plus 1 over 189. But then in the end, we get a negative sign. It's going to be negative 13 over 1728 z cubed. And that's going to be the modulus of z being less than 3, the smaller domain. That's the Taylor series expansion for this function about z equals 0. It's also the Laurent series expansion for this function about z equals 0. When a function is analytic at a point, the Laurent series expansion is the same as the Taylor series expansion. It's nothing new. Let's check this with series. Put the function in there. Z is the variable. 0 is what I'm expanding about. The highest power of z that I want to see before the big O comes next. Let's put 3 there so it matches. Did it work? Yeah, it looks good. Okay. Pretty cool. Always happy when this works out, right? How about if could we find the series for these things and multiply them? Yeah, we could. In fact, I could probably just modify my work over there a bit. Z over z plus 4 is the first product. Looking back over here, I'm looking at this thing now. Z over z plus 4, that's going to make it z over 7 divided by that. A is z over 7, R is negative z over 4. We get z over 7 plus z over 7 times negative z over 4 plus z over 7 times negative z over 4 squared, etc. I'll just do up to the squared terms this time. Does that look good? You think it's a mistake?
Where's the 7 coming from? Because did you erase the 4/7?
It was a 4/7 before. I was thinking I could just replace it. Oh, okay, yeah, okay. Thanks. But it should be a z over 4, right? Yeah. Does that look good now? Simplify a little bit. Actually, we're going to get the cube term when we simplify. Z over 4 minus z squared over 16 plus z cubed over 64. That's going to be true when, once again, if the modulus of z is less than 4. The other one, let's put a 1 in here, which is going to give us, careful here, a negative 1/3, right? Let's double check that. So a is negative 1/3, r is z over 3. Simplifies to negative 1/3 minus 1/9 z minus 1/27 z squared. If the modulus of z is less than 3, let's now multiply these series. The book calls this a quotient product, which is just a formal description of how to multiply series, even if you're ignoring issues of convergence. But you don't have to memorize the formula for the quotient product. Instead, you can just think about it here. Product of the series. Here's the way I would think about it. Are there any constant terms when I multiply these two things? No, there aren't. The lowest power is going to be a z power, first power, and that's going to come from negative 1/3 times z over 4, which is negative 1/12 z. As it should be. What things are going to give us the z squared term when I multiply these two things? I get a z squared from this times this. 1/4 times negative 1/9 would be negative 1/36. Product of these two things, I'll get a z squared term from the product of these two things. I'll get a negative 1/3 times negative 1/16 plus 1/48. Any other z squared terms? I did product of these two and the product of these two. Nothing else is going to give you a z squared. So the coefficient of z squared should be 1/48 minus 1/36. Is that the same as negative 1 over 44? 1/48 minus 1/36. That should be what, 3 over 144 minus 4 over 144 is negative 1 over 144, just like it should be. Let's go ahead and try the z cube term. It does get trickier as the powers get higher. You can get a z cubed from the product of these two. Negative 1/3 times positive 1/64. That will be negative 1 over 192. Again, keep going through the algebra in your head with me here so you find mistakes again. Product of these two will give a z cubed. Negative 1/16 times negative 1/9 is positive 1 over 144. And then I'll also get a z cubed from the product of these two. 1/4 times negative 127 would be negative 1 over 108. Hopefully that combines to negative 13 over 1728. Negative 1 over 192 plus 1 over 144 minus 1 over 108. Negative 13 over 1728. Got a match there. That. Okay? So we can do it that way too. Again, the domain of convergence is the smaller one. It's a disk of radius 3 centered at the origin here. About like that. Is it possible that I could find a series expansion for this, say, well, maybe in a ring centered at 0, between the circle of radius 3 and the circle of radius 4? Pretend this drawing is better than it is. Could I find an expansion for this original function in such a ring? Well, certainly, let's go back to the partial fraction expansion. Certainly in such a ring, I could get convergence for the series for this one, the Taylor series for that one, about 0. I'm not going to get the Taylor series expansion for this one about 0 to converge in such a ring, but maybe there's something else I can do. Let's use Mathematica to go a little faster now. So again, let's go back to the original partial fraction expansion of the function. There it is. So again, I said with a over z plus 4, which is the 4/7 over z plus 4, there shouldn't be any problem in the blue annulus to get the series expansion. It's the same as what I got before, and I erased it over there on the left side of the board. Taylor series for that one about 0 starts this way. And that should be the same as what I had over here, but I erased. Does it look right, Lauren? Okay. So that part's the same. But the series that I have for 1 over z minus 3 won't work, because that converges on a disk of radius 3 centered at the origin. It's not going to converge on this annular region. There's something else that I can do. Go back to 3/7 over z minus 3. I'd like to see if I can expand this in a series that instead of converging on an open disk centered at the origin, maybe converges outside the open disk of radius 3 centered at the origin. So maybe instead of getting it in terms of powers of z over 3, I wonder if I could get it in powers of 3 over z. How about factoring the z out of the bottom and writing this function this way? It's not going to be valid in z equals 0 to do that. But I'm not worried about z equals 0. I'm trying to get convergence in that annulus. This is of the form a over 1 minus r. A is 3 over 7z, and r is 3 over z. This is going to be 3 over 7z plus 3 over 7z times 3 over z, a plus a times r, plus a times r squared, etc. 3 over 7z plus 9 over 7z squared plus 27 over 7z cubed, etc. And that's going to converge if, once again, the common ratio, which is 3 over z, is less than 1 modulus, which is equivalent to the modulus of z being greater than 3. It's going to converge outside the disk of radius 3 centered at the origin. It's a Laurent series. It's not a Taylor series. Right? Taylor series, you need positive powers of z, or non-negative powers of z. Here we have negative powers of z, really. I could write this as 3/7 z to the negative 1, plus 9/7 z to the negative 2, plus 27/7 z to the negative 3. It's not a Taylor series. To give it a new name, we call it a Laurent series for this function centered at z equals 3. And it converges outside the disk of radius 3, centered at the origin. If I now combine these two series, I do get the series for the original function, the Laurent series, that contains both positive and negative powers of z, and converges on the common domain where both of these things converge, which is this annular region in blue here. Is there a way I can check that this Laurent series is correct? Let me give this function a name. Call it g of z. Just this one here. And let me let's say h of z be g of 1 over z. This works when we're expanding about z equals 0. And let's find the series for h of z centered at 0. And the coefficients, 3 sevenths, 9 sevenths, 27 sevenths, are the exact same thing that I got here. If I'm expanding about z equals 0 for this function in a Laurent series, converging in a disk, or excuse me, on the outside of the disk radius 3 centimeters of the origin, and I let h of z be g of 1 over z, then h will be a function that's analytic at z equals 0. Even though you'd be dividing by 0 there, don't worry about the seeming contradiction with that. And the series, the Taylor series for h centered at 0 will have the same coefficients as this series does. So that's a way to check it. Can we visualize this? Well, kind of, not fully, because graphs of complex value functions of our complex variable are really in 4-dimensional space, and we can't visualize 4-dimensional space. But we can try to visualize the real and imaginary parts. We can try to visualize the modulus or the argument. Let's try to visualize the modulus of this thing. So I can use Plot3D. Mathematica modulus is absolute value, ABS. The original function is what I'm doing here. I'm plugging in my arbitrary complex function as a function of the real part x and the imaginary part y. I'm going to type in x plus I times y. Go from -5 to 5. There we have it. And you see the poles, right? And -4 and +3. If I change my plot range, they really do look more like poles. Do a click bigger plot range. Now they're looking more like poles. Kind of that one's kind of spiky. It shouldn't be there. Right? Maybe if we plot more points, that will go away. That's better. So this is a graph of the modulus of f of z. Right? It goes to infinity as you approach negative z equals -4 or z equals +3. How about, okay, let's first do the Taylor series here. Let's see. Is there a pattern to those coefficients? If there is, I'm not sure what it is. And I'm going to try to find out. Let's see. There is a simpler pattern for each piece, though. Actually, let's. It's going to take too long if I try to do this too much. Let's try the Laurent series. The full Laurent series in general would be written in summation form like this. Here's the general form of the Laurent series. J goes from, you ready for this? -infinity to infinity. A sub j, z minus z0 to the j power. Define what that really means, though. you really typically break it into two parts. You typically break it into parts where j is non-negative. That's the Taylor series part, so to speak. Plus a series where j is non-positive. You may prefer you to use a different index of summation. Call it k maybe. K goes from 1 to infinity. And call this a sub negative k. And make this power be negative k. Both of these series would need to converge in terms of their partial sums, and you need to add them for this to make sense. Do a similar kind of thing with improper intervals going from minus infinity to infinity. Break it into two pieces in general like this. These two parts could be thought of as being the pieces on the annulus. We are focused on the annulus here. This thing, and those do have patterns that I could get into Mathematica pretty nicely. So let's do that here. Let's let S sub n of x, or of z I should say, be the nth partial sum of that series. Oh, this is the one where we were doing the product, wasn't it? That was the one where we were doing the product. I'd prefer doing the sum, but let me copy and paste the series for that down here. So I'm not doing this series. Okay. And this is the series for 4 sevenths over z plus 4, which when added to 3 sevenths over z minus 3 was the original function. I'm going to add the series here. I probably could multiply them, but I'm going to add them here. So the pattern here, k goes from 0 to n, is what? 1/7 times negative z over 4 to the k. Is that right? When k is 0, it gives you 1/7. When k is 1, we do get a minus sign there. We get z to the first power. 4 to the first is 4. 4 times 7 is 28. When k is 2, we get a positive z squared. 4 squared is 16. 16 times 7 is 112, right? Yep. I think this is right. So there's the partial sum for that series. What about the partial sum, not for the Taylor series of the other function, but instead it's Laurent series centered at 0? I'm switching around the j's and the k's, but don't worry about that. This series here, I'm going to use this one. 3 over 7 z is a, and r is 3 over z. Well, let me switch the j and k back around. Not a big deal, but just because. The sum of these two things would then sort of be a combined partial sum for the Laurent series of the original function that's going to converge on this disk. Hopefully. What should I call the combined series? How about capital S sub n? That'll be little s sub n of z plus t sub n of z. And what am I going to try to do here? I'm going to try to combine some plots. I'm going to try to make an animation showing convergence. Let's see here. Manipulate, show. What's going to be changing? It's the n that's going to be changing in manipulate. Get bigger and bigger partial sums, so to speak. Partial sums with more terms. If I just type something like this, n starts at say 1 and goes up to 10, that's not good enough because Mathematica will assume it's a continuous changing variable. If I wanted to go up by 1 each time, put an extra comma 1. So then I'm going to plot capital S sub n of z in modulus as well. ABS, capital S sub n of z. I need to type in, instead of a z, I need to type in x plus I times y. The same domain. I probably need to plot more points, perhaps. This might make it slower though. And I think I want to restrict the domain with region function. Well, maybe let's see what happens if I don't restrict the domain. I might need to make, let's see what this looks like. I might need to make the graphs more opaque so you can partially see through. Let's see what it looks like so far. It's not a mistake. Plot 3D, plot 3D. Do I have too many square brackets here? Is that the problem? Yeah, this should go inside plot 3D. There are two graphs there. Let's see, let's try making them somewhat opaque. What is that? Opacity, I think is the name for that. Opacity. No. Plot style, arrow opacity. They are both somewhat see-through. What's that hole in the middle, you might be wondering? That hole in the middle is there because of the partial sums, not because of the original function. The partial sums are converging on the angular region between two circles of radius 3 and 4. It's converging sort of in between where the poles of the original function are and where this sort of massive pole of this partial, it's not really a pole because we're talking about a partial sum here. Well, we still are dividing by 0 of 0, 0, so I guess it is sort of a like pole of the partial sum. This massive pole of the partial sum is occurring. So we're getting convergence in the annulus. The two graphs are getting closer and closer together. But elsewhere they're not. And that reminds me, the angular region does not go between these two things. It's outside of that pole. That was at z equals 3. So it's outside of that pole, but inside of this pole over here. That really convergence. If I try to use region function to restrict things, that might make it prettier. I'm not sure. Let's see. Region function. Arrow function. I think I got the syntax memorized here. x comma y comma, okay, if I want to be between the circle of radius 3 and the circle of radius 4, I want to be, if 9 is less than x squared plus y squared is less than 16. There we go, that's the graph of the partial sum. And it's not going to do anything weird here, because it's convergent to the original function on the disk that we're seeing here. So it's not really doing much weird. It's going to continue looking pretty much the same as n gets bigger, because it's approximating the original function. Really, we're looking at the graph of the modulus. If we looked at the graph of the argument, we should get convergence there as well. Dare I try that? I guess this one example is taking most of the time here. What if I graph the arguments of these things? What would happen? Inquiring minds want to know. Arg instead of abs. Probably a better plot range to use would be negative pi to pi. Right? Why is that negative sign projected? That's better. The argument, the principal value of the argument, goes between negative pi and pi. Oh, wow. So you see the full graph of the argument, the principal value of f of z is the bigger graph, and this is the partial sum, its argument. And as n gets, it's not exactly the other graph, you can see some differences there. But as n gets bigger, they should come closer together. It seems like some weird stuff's happening. Like it's small. It's doing lots of computations here. Let's wait for it. It might smooth it out. Wow, look at that. This makes me doubt the convergence. It doesn't look like it's doing it right. Some places it does, some places it doesn't. Maybe it's related to the fact that we're taking the principal value, we're taking a branch of the argument. Oh, okay, well, I explored. I'm not quite sure what was happening there, but I explored, right? We're exploring different things, seeing what happens. I could also look at the real and imaginary parts. I can graph those. Okay. We might as well, I guess. Right? We're so low on time as it is. What about the real and imaginary parts? Well, I want to use my capital RE function that I defined up here, which if you open a notebook, you wouldn't have this in it, but if you go to the notebooks online, you would. My capital RE that combines complex expand and capital R little e, and my capital I capital M that uses complex expand and capital I little m. I don't know why Mathematica doesn't have these commands in there anyway, but let's see. Did I just copy it? How about capital RE here? I think that should work. Guess it doesn't look that much different than the modulus. This would be harmonic though, whereas the modulus is not harmonic. They are slightly different. Again, as n increases, they should get closer and closer on the annulus, not elsewhere. And if I didn't use region function to restrict the domain, we'd get, I'm sure, them not being close together outside the annulus. Let me just mention one more thing. takes lots of practice, okay? So there's not a ton of journal problems that you'll be working on, but each one takes a while. So you got to practice this a lot over the weekend, and you may want to see if you can find some YouTube videos besides what I do here that show you more examples, because it just takes lots of practice. In a Laurent series expansion, the general form of it, if you're expanding about z0 like this, and if you get convergence on what you might call a degenerate annulus, a better name would be a punctured disk. If you get convergence on a set like this, that would be an open disk of radius r, take out z0. It's a punctured disk, sometimes called a deleted neighborhood of z0. If you get convergence on something like that, and if you include, if the AJs when j is less than 0, if some of them are negative, are non-zero, then you can classify the nature of the pole. If, for example, a sub negative 3 is the last non-zero coefficient for negative powers, meaning by last I mean when if j is negative 4, negative 5, or negative 6, that those AJs are 0. If this is the last non-zero one, then you can call this a pole of order 3. If there's a negative 4 that's the last one, then you can call it a pole of order 4. Okay, you can classify the poles. We're also going to relate this to integrals. And you'll see in the answer key for the journal problems that I often relate these things to integrals. I didn't have time for that today, but that's something you should think about over the weekend too, because exam 3 is in large part going to be about integration. Okay, so continue thinking about integration over the weekend as you look at these problems. See you on Monday.